Welcome to this presentation, and we hope you like and enjoy it. In this work, an autonomous robot platform is used as a tool for teaching and learning different disciplines and to prove that there are many hidden lessons beyond theory that can be learned using real experiences. The structure of the paper is as follows. Introducing robotic systems in the classroom engages students more deeply in the learning process and make them active learners. Working with them involves not only the knowledge of many different disciplines, but it is also an ideal platform to acquire other transversal skills. In this work, a twofold contribution is pursued. The proposed learning project involves the construction of the mobile robot, which is proposed with materials and resources that are easy to find and affordable. The main components of the robot are the ones of the blue text box. In this phase, it is especially important to place and calibrate the sensors well. Besides, a PID controller has been designed to control the real trajectory followed by the robot, measured by the infrared sensors. To assemble the mobile robot, the students are suggested to follow the flowchart of the left figure, but they can assemble the pieces in different ways in order to foster their creativity. Once the mobile robot has been built by work teams, it would be good to make the students think about the lessons learned during this task to develop a very important skill, critical thinking. Some of the possible conclusions they could reach, and that will lead them to consider lessons beyond the simple physical assembly of the robot, can be observed in the red text box. The scenario for the robot navigation is a maze. It can be used as an ideal way to train and improve the ability of autonomous robots to move around the environment. To obtain an optimal route, decision-making algorithms adapted to this specific situation are used. The maze proposed has been implemented virtually and physically. The designed maze and its specific variations is shown in the figures of the left. Its real and equivalent counterpart is shown in the picture of the right. The goal of this part of the project is to have the students code various maze-solving algorithms and compare the results in terms of efficiency and computational time. Uninformed algorithms, without any prior knowledge, explore the search space as they navigate the maze. Among them, two simple and easy to understand ones have been selected: random or mouse algorithm, and word follower. As part of the tasks left to the student's free choice, other algorithms can be suggested within this group, such as the pledge or Tremox. The behavior of the left-hand rule algorithm can be observed. The robot will move from one square to another, stopping at the black marks that serve to be aware of its position on the maze. And at every stop, the robot will take note of the obstacles that it encounters at its left, front, and right position in order of preference move direction. Also, it can be observed that the robot fixes possible line trajectory deviations thanks to the PID controller. Finally, when it arrives at the goal, the robot will stop at the marked spot, finishing its movement. With informed algorithms, the robot uses domain-specific knowledge. Therefore, these maze-solver algorithms are faster than those without additional information, as they have to explore a smaller search space. Again, two informed maze algorithms are proposed to the students. Optimized wall forward. Using the left-hand rule strategy, the optimization rules for the robot will be, in this particular case, the ones that can be observed in white text boxes. In this video, the flat fill algorithm can be observed. Now, the robot will only stop at the black marks to be aware of its position on the maze, not to check its surrounding obstacles. First, the algorithm will be passed to the Arduino board, and only when it encounters the best optimal path to follow, the robot will move swiftly through the maze and towards the goal. Notice how much navigation time is saved from the left-hand rule algorithm. Those four search algorithms have been tested on the same maze, with the obstacles fixed and being the optimal path 8 cells, as seen in previous slides. Random or mouse algorithm. Its randomness implies that it can vary between obtaining an optimal route or following the worst possible. And wolf-follower. The robot does not navigate randomly through the maze, but with a preferential direction set in advance, which avoids errors and thus reaches the goal much sooner. Results, time and iterations are much better than with random algorithm. Optimized wolf-follower. With it, if the robot knew where the obstacles are and it could navigate at its maximum speed, times would be significantly shortened. And flat fill. This algorithm requires more time than the others because it explores all possibilities before finding the optimal path. The navigation through the maze, in the virtual case, is immediate, and in the real maze more time is required due to the delay of the sensors, turns it takes, etc. However, it is a very efficient method, and the time to explore the labyrinth will be much shorter if some information on the maze is available. The results of the maze-solving algorithms average values in the case of the mouse algorithm in both the virtual and the real maze are shown in the next table. From these results, the following conclusions can be drawn. The result of this analysis and what the numbers say is that the flat fill algorithm is the best of all the algorithms tested, with the same maze, the same robot, and in the same conditions. There are several aspects that can be pointed out to awaken the critical thinking of the students and to make them think and draw conclusions about the experiences. First, regarding the operation of the robot, and then regarding the algorithms. So, the following possible improvements for the robot can be explored. A mobile robot is a learning platform not only to learn lessons closely related to robotics or other technological subjects. The mobile robot allows students to face real problems. Working with a real system allows to learn lessons that go beyond theory. Hope that you have enjoyed the presentation and our work. Thank you for your time, patience, and attention.